Okay, good morning. Let's begin. I wanted to begin by letting you know that as per the course schedule that's posted online, the class on Tuesday is going to be a recorded lecture that I'll post on YouTube. So we won't actually meet together on Tuesday of next week. And the reason for that is I'm conducting an ABET assessment of another university. So I'll be here, I'll be on campus, but I'm just going to be in video meetings all day long, so we can't have class. But I'll post the lecture on YouTube, and the link will be available on Blackboard, and I'll also email it to you, similar to what we did at the beginning of the semester. Your next homework assignment is due on Tuesday of next week, and so I imagine you'll probably spend some time on the weekend working on that. It's easiest for me to understand what you've done if you take a picture of your work. Like if you've been doing a bunch of calculations and then you have to write, like you're typing a message in the English language. First, I multiplied, like it's just awkward to describe in a narrative form what is like more obviously and more naturally expressed in equations. And so if you just want to send me a picture of your work and show me what you're stuck on, then I'll understand so much easier and faster than and it'll save you having to type it all out. So just a suggestion there. And also sometimes I'll be out and about, like maybe I'm at the movies waiting for the show to begin. If you send me also like a picture of the problem you're working on, then that'll allow me to answer you before I can get back to my notes and look up like what's the actual problem. Because sometimes people say, on problem number 1, and I don't really remember what's problem number 1, but if you send me a picture of the problem and also your solution up to that point, then I'll answer you wherever I am. If I'm in the middle of a hike, I'll just stop for a second and try and answer your question. All right, so your assignment's due on Tuesday before 11. Even though we won't have class on Tuesday, the submission deadline's still set to 11 for that. Any questions on the announcements? I wanted to also point out something. It's not immediately new. It's something I did maybe last week or the week before. But on Blackboard, there's the equation sheet for our exam. And so you can begin to familiarize yourself with the formulas that will be available to you during our tests.
Dr. Wood, the board is not.
Well, that would be useful. Thanks for letting me know. I wonder how long I would have gone without... See, I can see it, so you can't see it?
No,
all right.
That's what I was thinking.
Yeah. Very good. I appreciate that. At least my fly's not down, so far as we know. Yeah. Standing behind the podium's a good thing. All right, there it is. All right, so class on Tuesday is online. Homework 3 is due at 11 o'clock on Tuesday. Now, here on Blackboard, it's just in the main content folder. I really try and have a very simple Blackboard with just the content and the grades. That's it. So here on the content tab, you can find the exam equation sheet. And it's just 2 pages long. So if you want to begin to familiarize yourself with that. And then also is a sample exam. I think I've mentioned this before. So here's just 3 questions. That's what I would usually give during a 50-minute class. Since we have 75 minutes, I may give you 4 questions. Just because then, if you bomb one of them, that's only a quarter of your grade instead of a third of your grade. So it gives you maybe more opportunity to show what you know. And of course, I give partial credit as much as I can. When you show your calculations and you write the formula and the substitutions, when you give me a detailed solution, then I'm able to find things that I like in what you did and give you more partial credit on the exams. But when it's just the final answer without a lot of supporting detail, that's when it gets a little bit difficult to justify much partial credit. All right, so I wanted to point those things out. And then one other announcement is related to an upcoming career expo. And so if you're interested in getting an internship or doing co-op, or even thinking about when you might graduate someday, the full-time job that you would like to have, on October 13th, they're going to have engineering employers over at the Don Morris Room from 11 till 2. Last year, they made people pre-register for this event on Handshake, and I think maybe because of COVID restrictions, they were limiting how many people they let into the room at any time. I called over to the career education office this morning, and they told me that they're not doing it this year, that it's just kind of first come, first serve, everybody's welcome. Of course, you got to wear a mask, but when we have more information such as which employers will be there, I'll pass it along. But I think it's a great idea to plan to be there, because the employers that are at that career expo are anxious to have people applying. So it's kind of like, rather than sending out your resume cold to people who may or may not be interested, these people are definitely interested. All right, so where we left off on Tuesday, we worked through 4 examples. And remember, we started with the simplest case of a vertically oriented gate that began at the water surface. Example 2 was a vertically oriented gate that was beneath the water surface. Let me just refer back to those. We'll take a look at them again and try and recall why they became progressively more difficult. So this one was simple in part because delta H and Y bar are the same, because it's vertically oriented. Remember, Y bar is the inclined distance from the centroid to the water surface, and if it's vertically oriented plate like this one, then Y bar equals delta H. So that's part of what made this easy. Also, when it's vertically oriented, you're not going to have as much of the trigonometry to try and find out Y bar distances. So that's another aspect of why this was simple. Okay, example 2 was a little more complex. In this one, it's a vertically oriented gate, which is easy, but because it was beneath the water surface, we just had a little bit more analysis of the dimensions we had to do to find out delta H. You know, you had to take the overall distance of 6 meters and break that down to 3 meters from the shaft to the bottom of the gate, 3 meters from the shaft up to the water surface. Obviously, this drawing isn't to scale, which is always a little bit tricky. You can't assume that it's to scale, but the dimensions were given. So again, we applied the same approach here, where we, number 1, found delta H, depth to the centroid. Number 2, found the pressure at the centroid, P bar. And then the magnitude of the hydrostatic force was the pressure at the centroid multiplied by the area. Now finally, the location of the hydrostatic force we define using the YCP, which is the depth to the center of pressure. And here, the YCP is along a vertical path to the water surface. Now, there actually isn't water above the gate. There's concrete above the gate. I'm surprised nobody asked me about that, actually. So, from the centroid to the water surface is what I've said a couple of times before. But if you go straight up from the centroid to this gate, you never get to the water surface. So what we did was we extended where the water surface would be if the water surface continued horizontally beyond its bounds. So here's where the water surface would be if it extended sideways. Let me just do that to a dashed line. I don't know why. It's like, you know, some people don't like to step on a crack in the sidewalk. Sometimes I just get a little bit too obsessed with the formatting of these shapes. I'm just going to have to find a way to let it go. Because, anyways, you see where the water line would be if it extended over horizontally. So the delta H would be from the centroid up to this location. So you just extend the water surface sideways. Make sense? Okay, because there actually isn't any water above the gate. There's water to the side of the gate, but not directly above it. But that's okay because it doesn't matter. What it's really all about is what's the pressure at the centroid. And the pressure at the centroid is going to be the same if there is water straight above it or if you have to go sideways and then up. Because remember, when you go sideways, the pressure isn't changing. So it's okay that we have to go a little bit sideways and then go up to the water surface. Because that horizontal movement from one location to the other doesn't affect the pressure at the centroid. So this was the second example that we worked through. Lessons learned. Here was the third, and what made this next one a little bit tricky was now it's inclined. And now when the plate is inclined, this is when Y bar and delta H differ. They're going to be different because the centroid here, from the side view we can identify the centroid. It's right where the cursor is located. And so delta H is straight up to the water surface, whereas Y bar is the inclined path to the surface. So from the angle and the given depth to the edge of the plate is how we found both delta H and the Y bar. Any questions that maybe arise at this point as we're reviewing through these examples that we looked at last time? All right, the last one we didn't have loads of time to look at. I kind of showed you the solution for this one, but we didn't look at it in a lot of detail. But remember, with this one, the key was sort of this geometry that it's a 3, 4, 5 triangle, so that what I did in the solution was I said, let's relate the angle that this gate is oriented, it being a 3, 4, 5 triangle, so that the angle that the gate is oriented is going to be the same angle that Y bar experiences. Okay, now, does everybody see that the vertical depth, that the delta H is 10 meters? Because it's, so the vertical depth to the centroid, it's the 8 is the depth to the hinge, and then the vertical component of this 5 meter depth is 2 meters, because you know the 4 meter pipe, so vertically from the top of the hinge to the bottom of the gate is 2 meters, and so it's 2 meters downward from the hinge to the center of the gate, the centroid. So delta H is 10 meters, and that's the vertical component. So back to this, I'm saying there's some vertical component that's 10 meters, and I want to know what's the hypotenuse of this equivalent triangle. So what's the inclined distance that corresponds to the vertical component of that triangle? So then I did this similar triangles. I said, let 5 equal Y bar and 4 equal 10 in this similar triangles. And so the ratio of 10 to 4 is the same as the ratio of Y bar to 5. And that's how I found that inclined distance to the centroid, Y bar. All right. So here's what we're going to do today. I have a couple of problems that I printed them out. I'm going to hand them out to you here on the paper. And I'd like you to not work alone. I'm going to require that you scoot next to at least one other student and talk through this solution together. For the first one, we want to know what's the hydrostatic force on this circular plate. And it's a circular plate. Why from the front view does it not look circular? This looks elliptical from the front view. But I'm telling you it's circular. So why does it look elliptical? Because what?
Inclined.
I can't hear you.
Because it's inclined.
Because it's inclined. That's exactly right. Yes. Because we're looking at it from an angle. So when you look at a circle from an angle, it's not going to appear as though it's a circle. Okay, so let's just go through the front page yet, so far. So you're going to scoot over and work with these two? You're going to scoot over and work with him? All right, so we're going to collaborate on this one. And I've given you the step-by-step. Step 1, depth to the centroid. 2, magnitude of the force. 3, area moment of inertia. 4, location of the hydrostatic force. Now, there's oftentimes more than one way to visualize the geometry, and so you don't necessarily have to do it the same way that I did to get the right answer. But for this first problem, here it is. All right, so we have 6 meters vertically down from the water surface to the top edge of the gate, and you can see that I've drawn a triangle, following the same inclined path up to the water surface, and I'm just calling that distance x. X is the inclined distance from the water surface to the top edge of the plate. And so I ended up finding y bar before delta h, simply because I knew that y bar would be relatively easy because it's going to be half the diameter, because it's from the center to the top edge, and so it's the 2.764 divided by 2 plus x, where x is just some unknown distance from the edge of the plate up to the water surface. And then to calculate x, I use the idea that the orientation of this plate in the water, the angle is defined by a 3, 4, 5 triangle, and so the x distance is equivalent, the ratio of the hypotenuse to the vertical component, so x to 6, is the same ratio as the hypotenuse, 5, to the vertical component, 4, of this triangle. So that gave me the distance along the inclined path as being 7.5 meters, and then you can find the y bar is 8.882 meters. So then once I've got y bar defined as 8.882, I want to find delta h. And so that's like saying hypotenuse and vertical component. And so the ratio of delta h to y bar is the same ratio as x, which was this vertical component, 6 to x, which was the horizontal component that I'd found previously. So it turns out that the delta h is 7.1056 meters. And you could have gone the other way. And I know some people did and were successful with that, where they found the delta h first. So they said it's going to be 6 for delta h plus half of whatever the vertical component of that distance to the centroid is. And so the distance to the centroid along the inclined path is 2.764 divided by 2. That's the inclined distance, but we want to know what is the vertical component of that inclined distance. And so some people use that approach to find delta h, and then once delta h was defined, determined y bar. So that is part 1, depth of the centroid. Magnitude of the force is going to be the pressure at the centroid times the area. And for a plate like this, which is circular, it turns out that the cross-sectional area is 6 meters squared. I think that's maybe how I decided what the radius of this was. It was whatever radius gave you exactly 6 meters squared. And then the pressure of the centroid is the depth of the centroid, delta H times gamma. So you can see what calculations we went through to get the 418 kilonewton magnitude of the hydrostatic force. Area moment of inertia for a circle is pi r to the 4th divided by 4. Area moment of inertia about a horizontal axis should always have units of length to the 4th power. So it's 2.865 meters to the fourth. And then lastly, if you want to find the location of the force, that's essentially saying define where the force is applied relative to some datum. So the easiest thing for us to do is saying, what is YCP? What's the distance from the water surface down to the center of pressure, which is actually where the force is applied? Okay, so that is Y bar plus I divided by Y bar A. Let me leave this up for a second. Are there any questions related to this solution, or maybe the method more generally that you need to follow to find the hydrostatic force? All right, so the second problem, I know some of you have already gotten started on it, others haven't yet, and that's okay. We've got a 2-meter wide gate. We don't have a side view, but the text of the problem is telling you how wide the gate is. Remind me, for AB cubed divided by 12, what's A and what's B? How do we remember which term gets cubed when we're doing the area moment of inertia? B is the vertical component. Very good, that's right. So here, A is 2 meters and B is 6 meters when we get to the area moment of inertia part. Okay, so I'm asking you to determine depth of the centroid, pressure at the centroid, magnitude of the force, Y bar, and I think on your paper it also asks, and I just took a screenshot of the first part of it, your paper it also asks the distance between the centroid and the center of pressure, so YCP minus Y bar, and then the sum of the moments about the hinge. All right, so let me pause for a moment, and I'd like you to, again, collaborate with your classmates on this one. Talk through it together. Okay, let's look at the solution. I'm going to bring it up on the screen here in a second. On the whiteboard, I drew a little bit more detail about the geometry that applies for calculating the delta H and the Y bar. Hopefully that's useful, but let's just take a look at the first part of this. Okay, so you can see that this gate is following a 30-degree incline. And so what that means is that if we extend that same path, we can rejoin where the path would intersect the water surface. And so, there isn't water above the gate. So the pressure that's acting on the gate, we have to go sideways and then up, is what's causing the pressure acting on the gate. So think about what the water is doing. The water is pushing the gate towards that stop. So the hydrostatic force is kind of pushing the gate sideways and up because of the way the gate is oriented. So it's pretty obvious from inspection, we can just look at it and see that from A down to the stop is 6 meters total. So from A to the centroid will be 3. So that's from A to the center of area of the gate. And so then if we want to know Y bar, then we're going to have to find from A up to the water surface. The first thing it asked for, though, was the depth of the centroid. And so that's the vertical distance from the water surface down to this center of area. So it's 3 meters. And then it's going to be less than 3 meters because from A to the centroid along the inclined path is 3 meters. And so the vertical component of that will be just 3 meters multiplied by the cosine of 30 to find out the vertical component of the inclined path. Okay, so delta H is 5.598 meters. The pressure at the centroid, we'll just multiply the unit weight by that to find 54,000 newtons per meter squared. Magnitude of the force is where we multiply the pressure at the centroid by the area of the gate, and it's a 2 by 6 meter gate, rectangular in shape. The inclined distance to the centroid, so 3 meters from A to the edge plus more than 3 meters, because if the vertical component of this distance was 3, then the hypotenuse will have to be larger than that. So you can see here I'm saying it's 3 divided by the cosine of 30 to find that distance. So 6.464 meters. And then I ask you to determine the distance between the centroid and the center of pressure. So the centroid is depicted here with the dot. The center of pressure will be below that. And the reason why I think that's the useful dimension to have rather than calculating YCP is that we're going to be doing a moment analysis about A. So, how far it is up to the water surface really isn't as significant as the distance to the hinge point that we're going to do the moment analysis to. And so if we can find how far it is from the centroid to the center of pressure, then all we need to do is add 3 meters to that, and we found the counterclockwise rotation moment distance. Okay, so for a rectangular gate, we determined the area moment of inertia is 36 meters to the fourth because we've cubed the vertical component, the vertical dimension of 6 meters, cubed, divided by 12, multiplied by 2. So this is just kind of a reconfiguration of the formula for YCP. If we were finding YCP by itself, we would have added y bar to the right-hand side of the equation, but instead, we're just going to have I divided by y bar A to give us that gap distance between the centroid and where the force is applied. So that gap distance is 0.4641 meters. And so in the final estimation here, you can see what I'm saying is overall the distance from the hinge point to the block is 6 meters, and the gap is 0.4641 from the centroid to where the force is applied. So then the moment distance for the counterclockwise rotation will be 3 plus that gap distance. And then we know the hydrostatic force magnitude, and we know the clockwise distance, the clockwise rotation distance, and the only unknown then would be what force is resisting the hydrostatic force of the gate. So the force of the block is going to be less than the hydrostatic force because the moment distance is longer from the hinge point to where the block is applying it. So the stop is only experiencing a force of 380 kilonewtons. Okay. What if a plate is vertically oriented? It's easy because it's delta H and y bar equal. We tipped over a plate in one of our other examples, and the one we just worked, it was at an angle. And then the other extreme is if it's horizontally oriented. So we can still follow the same method if it's horizontally oriented as we do in the other approach, where we find the depth to the centroid. So what's the depth to the centroid here? Delta H is 5 meters. Okay, so then the magnitude of the force would be delta H times gamma times the area. So the magnitude of the force would be 5 meters. If this is in water, it says it's flat in the water, so then the 9810 newtons per meter cubed. And then the area of this plate is 3 by 2, so that's 6 meters squared. Can someone calculate what's 5 times the unit weight of water times 6? Should be around, I think.
294,300.
How much?
294,300.
Okay. So this is the hydrostatic force that we determined by multiplying the pressure at the centroid by the area. What if we just found out what's the weight of the water above the plate? So a different way of looking at this same issue is we've got a plate in the water. Let me see if I can draw in 3 dimensions. This usually doesn't end well. But we've got a plate in the water, and it's 2 by 3. Maybe better than that. All right, 2 by 3, and there's this water above it. Okay, so how much water is above it if it's 5 meters down beneath the water surface? So think about a box of water. There's essentially a box of water above this rectangular plate. And so the weight of the water would be the volume multiplied by the unit weight. And so the volume that's above this rectangular shape is 2 meters by 3 meters by 5 meters. And if we want to find the weight of water above the plate, we just multiply that by 9810 newtons per meter cubed. Okay, so we found it according to the hydrostatic force method. And then this next way we find the weight of the water, which is the volume multiplied by the unit weight. Okay, so it's 2 by 3 by 5, which is 30 cubic meters, and multiply that by 9810, and lo and behold, the weight of the water above this flat plate is the same force that we calculated according to the hydrostatic method approach. So what we can draw from that is that the vertical forces that are acting on a submerged object are equal to the weight of the water above it. So let me type that out. Oh, I already did. The weight of the water is equal to the vertical component of the hydrostatic force. All right. So this is a hint of what we're going to be doing once the shapes get curved. So far, all of the gates that you've been working at were flat gates. But what if there was a gate under the water that wasn't flat? You know, because it is possible to bend metal. Metal isn't always just flat. You could have, here's the water surface, and you could have a gate that's curved so that maybe you've got this metal piece here that's curved in profile. And so what we want to know is, you know, like, what's the hydrostatic forces that are acting on this bent gate? And what we did before isn't enough. We have, you know, there's some additional considerations because there's a vertical component of the force and also a horizontal component of the force. So what I've just put on the screen here, where this horizontal plate, the lesson that we learned from this analysis is that the weight of the water is the vertical component of the hydrostatic force. And so that'll also apply when we've got curved gates. And that's going to be in that recorded lecture that I have for you on Tuesday, is what happens and how do we do the calculations for a gate that's curved. So just as a reminder before you go, remember homework number 3 is due on Tuesday at 11. Tuesday's class is online. And let me know if you need help on the assignment. I'd be glad to assist you in any way I can. Have a good day.